April 1945. A silver fighter screams across German skies at 490 miles per hour in a steep dive, chasing a Messerschmitt Bf 109 that's desperately trying to escape. The German pilot pushes his aircraft to its absolute limit. But it doesn't matter. The American P-51 Mustang behind him is faster, more maneuverable, and relentless. Within seconds, the gap closes. 6 50-caliber machine guns light up. Another Luftwaffe fighter falls from the sky. This scene played out hundreds of times in the final year of World War II. But here's what most people don't know. The P-51 Mustang shouldn't have existed at all. And when it was first built, it was actually a failure. The story of how this aircraft became the most feared fighter in the skies involves a material so revolutionary that it was initially considered too dangerous to use. A metallurgist who challenged every conventional wisdom of his time, and a series of accidents, chance meetings, and desperate gambles that would ultimately change the course of the war. This is the story of the forbidden alloy that made the impossible possible. Let's go back to early 1940. Britain is in trouble. The Luftwaffe is preparing for what will become the Battle of Britain, and the Royal Air Force is desperately short of fighters. They're losing aircraft faster than they can build them. Keyed, Spitfire is excellent, but production can't keep up with losses. Britain needs fighters, and they need them yesterday. Enter the British Purchasing Commission. In April 1940, they approach a relatively unknown American aircraft company called North American Aviation. The British don't want North American to design a new fighter. They just want them to build someone else's design under license. Specifically, the Curtiss P-40 Warhawk. But North American's vice president, a man named James Dutch Kindleberger, has other ideas. He tells the British something audacious. Give us 120 days, and we'll design you a better fighter from scratch. The British think he's insane. Design an entirely new fighter aircraft in 4 months? The industry standard is 2 to 3 years. But Kindleberger has a secret weapon. His chief designer, Edgar Schmude. Schmude is a German-born engineer who had worked for Fokker in Germany and later moved to America. He's been secretly sketching designs for a revolutionary fighter aircraft for months. He believes he can create something faster, more efficient, and more deadly than anything currently in the sky. But his design requires materials that most engineers consider too difficult, too expensive, or too dangerous to work with. At the heart of Schmude's vision is an airframe that needs to be simultaneously incredibly strong and impossibly light. Traditional aluminum was too weak for the stresses his design would generate. Steel was too heavy. He needed something else entirely. That something else was an aluminum alloy designated 24ST, later known as 2024 aluminum. To understand why this was revolutionary, you need to understand the problem with pure aluminum. Aluminum is wonderfully light, about a third the weight of steel. But it's also soft, weak, and completely unsuitable for aircraft that need to withstand enormous forces. Dive at 400 miles per hour, pure aluminum wings would fold up like paper. In 1906, a German metallurgist named Alfred Wilm had accidentally discovered something remarkable. While trying to harden aluminum alloys, he left some samples on his workbench over a weekend. When he returned and tested them on Monday, they had mysteriously become much harder and stronger without any additional treatment. He had stumbled upon what we now call age hardening or precipitation hardening. This led to the development of duralumin, an aluminum-copper alloy that was stronger than pure aluminum. But it still wasn't strong enough for the stresses that Schmude's design would generate. By the 1930s, metallurgists at Alcoa, the aluminum company of America, had refined this concept further. They created 24ST, an aluminum alloy that combined aluminum with copper as the primary alloying element, along with magnesium and manganese. The composition was approximately 93% aluminum, 4.4% copper, 1.5% magnesium, and 0.6% manganese. This alloy had a tensile strength of around 470 megapascals, roughly 68,000 pounds per square inch. Compare that to pure aluminum's 90 megapascals. It was more than 5 times stronger while remaining nearly as light. The strength-to-weight ratio was extraordinary. But here's the catch. 24Est was extremely difficult to work with. It was hard to form into complex shapes. It required precise heat treatment. Get the manufacturing process slightly wrong, and the material could develop microscopic cracks that would lead to catastrophic failure at high speeds. Many engineers called it temperamental. Some called it dangerous. A few called it forbidden, not because it was literally banned, but because working with it was considered career suicide if anything went wrong. Edgar Schmood didn't care. He knew that if he could master this material, he could build an aircraft that would redefine what was possible. May 1940. The clock is ticking. Edgar Schmood and his team at North American Aviation begin one of the most intense aircraft development programs in history. They're working around the clock, 7 days a week. Schmood's design philosophy is radically different from anything that came before. Every single decision is driven by one question: how do we reduce drag and maximize efficiency? First, the wing. Traditional aircraft wings at the time were thick and relatively blunt. They provided good lift, but created enormous drag at high speeds. Schmood designs something completely different: a laminar flow wing. This wing uses a new airfoil developed by the National Advisory Committee for Aeronautics, NACA. Instead of having its thickest point near the leading edge like traditional wings, the laminar flow airfoil has its maximum thickness further back, at about 40% of the chord. The result is that air flows smoothly over much more of the wing's surface before it becomes turbulent. Smooth, laminar airflow means dramatically less drag. Less drag means higher speed and greater range. But there's a problem. This wing design requires absolutely perfect construction. The surface has to be smooth to within thousandths of an inch. Any rivet head sticking up, any panel misalignments, any surface imperfections at all, and the laminar flow is destroyed. This is where 24ST aluminum becomes essential. The alloy is strong enough that Schmood can use thinner sheets, which are easier to form into the precise curves he needs. It's stiff enough that the wings won't flex and deform at high speeds, which would disrupt the laminar flow. And it's workable enough, if you have the right expertise, to achieve the precise tolerances required. But working with 24ST is brutally difficult. The sheets have to be carefully heat-treated, a process called solution heat treatment, followed by artificial aging. Heat the aluminum to around 920 degrees Fahrenheit, then quench it rapidly in water. This dissolves the alloying elements into the aluminum matrix. Then age it at a specific temperature, usually around 375 degrees, for several hours. During this aging process, microscopic copper aluminum precipitates form throughout the material, dramatically increasing its strength. Get any step wrong, and the material is worthless. Heat it too much during forming, and you undo the heat treatment. Cool it too slowly, and you don't get the right crystal structure. Age it incorrectly, and it won't develop full strength. And if you create any stress concentrations during manufacturing, those will become crack initiation points that can lead to catastrophic structural failure. Schmood's team has to develop entirely new manufacturing techniques. They create massive hydraulic presses to form the complex curves of the fuselage and wings. They develop new riveting techniques that don't create surface imperfections. They create detailed procedures for every single step of handling the 24T alloy. The radiator placement is another stroke of genius. Most fighters at this time hang their radiators underneath the fuselage like a bathtub, creating enormous drag. Schmood places the radiator behind the pilot with an innovative duct design. Air enters through an intake under the fuselage, passes through the radiator, is heated, and exits through a carefully designed outlet. The heated air expands and is actually accelerated, creating a small amount of forward thrust. This Meredith effect turns a drag-producing necessity into a slight advantage. The fuselage is narrow and streamlined, constructed entirely from 24T aluminum sheets. Every panel is carefully fitted. Every rivet is flush-mounted. The canopy is shaped to minimize turbulence. Even the landing gear is designed to retract completely into the wings, leaving no protrusions to create drag. September 9, 1940. Exactly 117 days after the contract was signed, the first prototype, designated NA-73X, is rolled out. 3 days under the deadline. It's a stunning achievement, one of the fastest aircraft development programs in history. But here's the embarrassing part. They don't have an engine yet. The Allison V1710 engine that's supposed to power it is delayed. So this beautiful, revolutionary airframe sits on the ground for over a month, waiting for its engine. October 26, 1940. The NA-73X finally takes its first flight, with test pilot Vance Breese at the controls. The flight lasts just 5 minutes, but it's enough to reveal something extraordinary. This aircraft is fast, really fast. Even with an engine that's not particularly powerful, the Mustang's low-drag design makes it one of the quickest aircraft in the sky. There's just one problem. A massive, critical problem that threatens to doom the entire program. The early P-51 Mustangs, powered by the Allison V1710 engine, are excellent aircraft at low altitude. Below 15,000 feet, they're fast and agile. They can outrun most German fighters at sea level. The RAF puts them into service quickly, using them for reconnaissance and ground attack missions. But above 15,000 feet, the Mustang transforms from a thoroughbred into a cart horse. The Allison engine simply can't produce power at high altitude. And in 1942, that's where the war is being fought. The issue is the supercharger, or rather, the lack of an adequate one. Every piston aircraft engine loses power as altitude increases because the air becomes thinner. There's less oxygen for combustion. To compensate, engines use superchargers, essentially air compressors driven by the engine itself, to force more air into the cylinders. The Allison V1710 has only a single-stage, single-speed supercharger. It works fine at low altitude, but as you climb higher, it can't maintain manifold pressure. By 20,000 feet, the engine is gasping for air, producing maybe 60% of its sea-level power. This is catastrophic because the Luftwaffe operates at high altitude. They're up at 25,000, 30,000 feet, diving down on Allied bombers. The Allison-powered Mustang can't even reach those altitudes with combat effectiveness, let alone fight there. The RAF is disappointed. The Americans are skeptical. The entire program seems destined to become a footnote, another promising design that didn't quite work out. The Mustang is relegated to low-altitude tactical reconnaissance missions. Important work, but not the war-winning fighter role it was designed for. Hundreds of these beautiful aircraft, with their revolutionary airframes constructed from that difficult, expensive 24T aluminum alloy, are performing admirably at low level, but failing to reach their true potential. It's like having a Formula One car with a lawnmower engine. Edgar Schmood knows his airframe is capable of far more. The structure can easily handle speeds well over 400 miles per hour. The 24T aluminum construction is proving incredibly strong and reliable. The laminar flow wings are working better than expected. Everything about the aircraft is excellent except the one thing Schmood didn't design: the engine. April 30th, 1942. This is the day that changes everything. A day that would take this underperforming aircraft and transform it into arguably the greatest fighter of World War II. Ronald Harker, a test pilot from Rolls-Royce's flight test establishment at Hucknall, is visiting the RAF's Air Fighting Development Unit at Duxford. The commanding officer, Wing Commander Ian Campbell-Ord, offers Harker the chance to fly one of their Mustang IS. Its aircraft number AG422. Harker takes it up and is absolutely blown away. The handling is superb. The visibility from the cockpit is excellent. The controls are responsive and well-balanced. The aircraft feels light and nimble, and the speed, even at low altitude with the underpowered Allison engine, is impressive. But Harker immediately recognizes what everyone else already knows. Above 15,000 feet, performance falls off a cliff. The Allison just can't cut it at altitude. Harker has a revolutionary thought. What if we took this magnificent airframe and married it to Britain's best engine? What if we put a Rolls-Royce Merlin in the Mustang? The Merlin is the engine that powers the Spitfire and the Hurricane. It's a masterpiece of engineering, particularly in its later variants with two-stage, two-speed supercharging. The two-stage supercharger compresses the air twice, first in a low-pressure stage, then in a high-pressure stage. Between the stages, an intercooler cools the compressed air, making it denser. This allows the Merlin to maintain high power output all the way up to 30,000 feet and beyond. Harker writes a report to Rolls-Royce suggesting this combination. The idea quickly gains traction. By July 1942, Rolls-Royce begins a feasibility study. In parallel, the U.S. Army Air Forces has the same idea and contracts North American Aviation to do the same thing in America using the Packard-built version of the Merlin. Two Mustang airframes are modified, one in Britain and one in America. The British aircraft, designated Mustang X, flies first on October 13, 1942. The results are stunning. With the Merlin 65 engine producing 1,620 horsepower with its two-stage supercharger, the Mustang's performance at altitude is transformed. The American modified aircraft, designated XP-51B, flies on November 30, 1942, with a Packard VD 1650 Merlin. The performance is equally spectacular. This is it. This is the combination that will change everything. What happens when you take an airframe designed with obsessive attention to drag reduction, constructed from advanced materials that provide incredible strength-to-weight ratio, and power it with one of the most sophisticated engines of the war? You get something that shouldn't be possible. According to the Aerodynamics textbooks of the time, the P-51B and P-51C Mustangs with the Packard Merlin engine begin production in 1943. The EIE performance figures are extraordinary. Maximum speed at 25,000 feet, 440 miles per hour. At high altitude, where the Allison-powered version was wheezing along at maybe 350 miles per hour, the Merlin-powered Mustang is doing 440 and still accelerating. But the real breakthrough isn't just speed. It's range. The Mustang's sleek, low-drag airframe constructed from precisely formed 24ST aluminum means it sips fuel compared to other fighters. Add in internal fuel tanks and then, brilliantly, external drop tanks that can be jettisoned when empty or when combat begins. And suddenly, you have a fighter that can fly from England to Berlin and back. Let me put this in perspective. In 1943, the maximum combat radius of most Allied fighters is maybe 400 miles. The P-51 Mustang with drop tanks? Over 1,000 miles. It can escort bombers deep into Germany. Fight.